We were looking at the phase domain model of the clock and data recovery circuit with forwarded clock. And the system for which we generated the model is this. We have the linear phase detector. We have a delay TD for the clock, and we use a charge pump on the up and down signals. Okay. And for this we found the model to be if the incremental, so it locks to some operating point, and over that if the incremental phase of data is phi d and this is phi ck in, so let me call this clock in and this is clock, then you will have increments in the control voltage as well as the clock phase. The model that relates all of these things we saw was this. We have some phase detector gain, which is density factor times ICP by 2 pi. This produces an average current ICP, which is a measure of the detected phase, which goes into a capacitor C to give you the control voltage, and this goes to a scaling Kd times omega naught, where Kd is the proportionality constant for the delay line and omega naught is the radian frequency of the, the basic corresponding to the data rate. To this you add the phase of the input clock and you close the loop. Okay. And we found the transfer functions phi ck by phi d, phi ck by phi ck in, as well as to this point you have additional stuff which I call IMCP. This corresponds to the random noise of the charge pump as well as the pulsed nature of the charge pump output, right? The charge pump output is not equal to average measure of phase detection, right? In addition to that, it has some square wave. It also appears here. Okay. It's not a big deal, but if you want to calculate the effect of the square wave, you can do this. In a phase lock loop, when you have a low frequency input, it's a bigger deal, as we will see later. Okay. And with this was a low pass transfer function. This was a high pass transfer function, and this this was also a low pass transfer function, right? It's the same transfer function as from phi d to phi ck, but there is an additional scaling factor. Okay, is this fine? So this is what we do with every phase domain model, phase domain model of any CDR. The first thing to do is to construct the phase domain model, and then you can evaluate different relevant transfer functions, and from there you can calculate different quantities that affect the synchronization. Okay, is this fine? Now I will show all those metrics with this. Some of them make more sense with when you don't have the forwarded clock, or they will not be such a big issue here, but there it may be a much bigger issue. Okay. So typically the things that you would measure with when you have a clock and data recovery circuit, what you are required to present are jitter tolerance. What this means is you apply jittery data, that is you apply a sinusoidal jitter to data, right, of different amplitudes, different jitter amplitudes. Okay, that is the edges of the input data will be sliding back and forth. The frequency of the jitter can vary and the amplitude of the jitter can vary. So for every frequency you go on increasing the amplitude of the jitter until the data is not recovered properly. I mean, the way you do it is you send a known sequence, and this clock and data recovery also recovers the data, right? So you measure the bit error rate. Okay, so bit error rate should be ideally 0, that is the output bit should be the same as the input bits, but in reality it won't be because of various reasons. First of all, you will not have infinite signal to noise ratio, right? So whenever you have finite signal to noise ratio, bit error rate will not be 0. So now so you will have some bit error rate when the clock is aligned perfectly with the data and the data has no jitter. Now when the data starts having jitter, what happens? So this clock here, if it is recovered properly, it should be in the middle of the data period. But as the data edges keep moving back and forth, this tracking will fail at some point. Okay, so it will track, but it may not keep it in the center, it will move away from the center. And if it moves sufficiently away from the center, what happens is it will start increasing the bit error rate. Okay. So the way you do it is you apply a jittery data of different frequencies. At each frequency you go on increasing the amplitude. At some point, so this I have not been showing the output here. So this phase detector also has the data output, right? The recovered data output. It is taken from one of the flip-flops in the phase detector. Okay. So you go on increasing the amplitude of the data until the bit error rate crosses a certain threshold. Okay, maybe your threshold is, let's say, 10 to the minus 12, and you go on increasing the bit error rate when you go on increasing the jitter until the bit error rate exceeds 10 to the minus 12. And you say that that value of jitter is what you can tolerate. Okay, so then you apply a jitter at a different frequency. Then again you go on increasing the amplitude of the jitter until the bit error rate crosses 10 to the minus 12. So then you again find the amount of jitter that can be tolerated and so on. Okay? Is this fine? So this is basically a measure of jitter in input data that can be tolerated, which means basically to maintain BER less than a certain threshold. Okay. Okay. Now when you have this forwarded clock, right, you have the data and you have the clock, and they are generated from the same transmitter. So in general you expect that the jitter in the data and clock will be correlated. They may not be exactly same, one of them may have slightly different jitter than the other, but they will be correlated. But for now let's assume that you jitter only the data and the clock is clean. Okay, and then you measure this. Like I said, some of these things make more sense when you don't have the forwarded clock at all. Okay. When you don't have the clock from the other side, this becomes a much bigger deal because you have to recover the only source of generating the clock is the data itself. Okay. So, but in this case, like assume that the input clock jitter is 0. Okay. So what do you think this will look like as you change the jitter frequencies? What will happen to jitter tolerance? Will jitter tolerance be high at low frequencies or high frequencies? Huh? It will be high at? Why? Yeah, so basically if the edges are moving around slowly, then the loop can track the edges. Okay. Now how do you calculate this? First we assume that the timing of the clock with respect to data, that is phi d minus phi ck. So this should be ideally 0. This is the increment, right, over the operating point. At the operating point, the clock is in the middle of the data, and now this phi d minus phi ck represents the skew in the data relative to the clock. This is the relevant thing, right? You want the clock to be in the center of the data, and you want the absolute value of this to be less than something. Okay, I don't know what it is, but let's say less than pi by 8 or some number. Okay, so that is, it is not exactly at the center, but it is not moving away from the center by more than a certain value. This I took as some number, but let's say it's whatever phase deviation you can tolerate. So if you go beyond this phase deviation, the bit error rate exceeds a certain value. Okay, so this is what you will have to calculate. So then how do you calculate this? So now you know that, you know what phi ck by phi d is. This is 1 by 1 plus s by omega naught. Okay. So what will be phi d minus phi ck? So this will be phi d minus phi ck by phi d would be s by omega naught by 1 plus s by omega naught. Okay. So now I want this to be less than delta phi max. This is the same as saying phi d times s by omega naught by 1 plus s by omega naught. I mean, I take the magnitude of this at that appropriate frequency. I substitute s equals j omega and so on. Should be less than delta phi max. Okay. So by the way, this assumption, like I said, phi ck in is at least partially correlated with phi d. So this is not quite true, but that's okay. We will see the application of this later. So now what happens? We want essentially to satisfy this requirement, this should be less than whatever phase deviation you can tolerate times, what is it? And you have to substitute s equals j omega, where omega is the jitter frequency. Okay. So if you plot now essentially this phi d, or which is basically termed jitter tolerance, this is the tolerable jitter, right? This phi d. Okay. Or rather this number is the tolerable jitter. And you plot this versus frequency, what will it look like? What will it be at very high frequencies? What is it? What is the value at very high frequencies? Delta phi max. Okay. And this makes sense. Essentially it says that if the data is jittering at a very high frequency, then the clock is not tracking at all. In fact, clock is not moving at all. Okay. So then it says that the the data jitter cannot be more than delta phi max, because because the clock is not moving, only data is moving, it can only move by delta phi max. Okay. Now what happens at lower frequencies? What's that? So no, what will be the shape of, if I plot this J12 versus this high pass? So this will rise like that, okay? Because obviously, I mean, at very high frequencies, 1 is negligible, this becomes 1, and at low frequencies, this is negligible and it becomes omega naught by S. So it increases as you go to lower frequencies, and this corner is omega, okay? So if you jitter it around very slowly, you can tolerate large amounts of jitter, okay? That absolute jitter can even be more than 1 cycle, right? So this is a common plot that you see, but again, like I would say, more a concern with when you don't have the forwarded clock, but you can calculate this. I mean, this can be done, right? This experiment also can be done. For instance, you have a system with a forwarded clock, you apply jitter only to the data and not the clock. If you measure it, this is what you will see. Okay? Is this clear? The definition of jitter tolerance and how to calculate it? Okay? Only one small modification here. Typically, there are different measures that are used for any of this jitter or any of this time related quantities, right? So let's say jitter, you can specify it in units of time, and this is what is usually called jitter or time jitter, okay? Or you can express it in phase, in radians, or typically you can also express it in unit intervals, that is the number of cycles, and this is basically, this is the unit interval, and this is nothing but phase divided by 2 pi, okay? And if you look at this jitter tolerance, you can express it in any of these things, but it's quite common to express it in terms of unit intervals, in which case you divide this by 2 pi, that's all, okay? So if you have to express it in unit intervals like this, this will be that divided by 2 pi. Is this okay? Any questions? So that is basically depends on your design, okay? So your design will behave some way as the clock moves away from the center, right? So that is the measure of that, huh? So basically, as you move away from the center, bitter rate starts increasing. The way you measure it is, you measure bitter rate. You are not looking at, I mean, you don't care about whether, see, in practice, you don't care about whether this is within 1 degree of that or 10 degrees of that. You care about getting a certain bitter rate, okay? So that is, you go on increasing the jitter amplitude until you hit a certain bitter rate. Of course, for calculation purposes, we can't calculate the bitter rate and do it. And also you know that if the clock is not at the center but very close to it, you are not likely to have a high bitter rate. So now I am saying the clock has to move by, I have changed the bitter rate criterion to this criterion. If the clock moves by this amount, delta phi max, let's say it is 5 by 8 or whatever amount, then the bitter rate will cross a certain value. So I have changed it to that one. Is this okay? So let me write this. So this is required for okay? Yeah. What's that? No. So now what I assumed is that for this whole calculation, right, I have assumed phi d is not 0, that is the data is jittery, and phi ck in is 0, that is clock is not jittery. Okay? We can do this experiment, but this is not likely to happen with the forwarded clock, right, because the clock and data are generated from the same transmitter. So the jitter will be at least partially correlated, if not fully. Okay. This is fine. I mean, phi d minus phi ck in also will not be very large because they are generated from the same transmitter and the same clock. Okay. But I mean, it's just to define this quantity known as jitter tolerance, I did that. So then there are other measures of jitter, basically how much jitter is transferred from the data to the output and so on. I'll look into it, we'll look into it afterwards when we get into the case without the forwarded clock. Okay. And one particular thing of interest is also jitter generation. Okay. So this is basically, let's say the input has no jitter, that is the input data has no jitter, input clock has no jitter. How much jitter will be there in the output clock? Will there be any jitter or no? Why? Huh? Yeah, so there is noise in the system basically. Your clock and data recovery circuit has noise, so that will create phase noise in the output clock. Okay? By CK in, not CK. So how would we calculate this? First of all, what are the things that contribute to this one? In this case, we basically have the charge pump noise and delay line noise, which can be expressed as phase noise, right? The delay will not be the same over time because of noise in the delay line transistors. You will have delay line noise also. The delay itself will keep changing. Then you also can have input referred noise or noise of the phase detector. The phase detector itself will have noise because it's supposed to be comparing edges, right? So whenever you have that, there will be some noise as well. Okay. Let me just take these two. So charge pump noise is this current INCP and delay line noise is, I'll call it phi ND, the phase noise of the delay line. Okay. And these can be modeled. I mean, this INCP I have already shown. It is added there, and the delay line phase noise will be added there. Okay. What this means is that you model the delay line like this. Okay. You have the input signal and there is a certain delay and you have the output. Okay. So this means that if the phase of the input clock is some theta ckn, the phase of the output clock should be theta ckn minus omega naught td. Right? Now in reality, if you will find that this is this plus some phi nd. Okay. So there will be some noise component to it. So that is the phase noise of the delay line. Is this okay? Any questions here? So then first of all, what you have to do is to find the transfer functions. pi ck by INCP. This we've already done. This is the gain preceding the addition of that current, and then you have a low pass transfer function. Okay? Is this fine? So now if you want to calculate the spectral density of this, that is spectral density of noise in pi ck, it will be spectral density of the charge from noise current, and this squared and the magnitude squared of this, which is if F naught is the same as omega naught but expressed in hertz, right? F naught is omega naught by 2 pi. Okay, so it will have some low pass shape, and if the charge from noise current is white, then you can calculate the variance also directly, right? Because it will be this, these parts will be frequency independent, and the integral of this is pi by 2 times F naught. Okay? So you can essentially, if you integrate this, you will get sigma square of pi c. And of course you can go on later express that in seconds or unit intervals or whatever you want. Is this okay? Now, what will be the noise of the charge pump? Let's just quickly look at it. So, you have two current sources. Controlled by switches. Now, the way this will be implemented is the upper one will be a PMOS source. Okay. So, this is a PMOS current source, and you will have a switch which is also a PMOS transistor like this. Now, this is not the only possible implementation. This switch can be on the other side of the current source also. Okay. In fact, that is preferred for various reasons sometimes. So, this is up and down. This is a PMOS switch, so this will be up bar, and similarly this will be down, and here we will have an NMOS current source. Okay. So now we can neglect the noise of the switches, and each of these current sources will have, of course, both are implementing a current source of value ICP. What will be the value of the noise? I mean value, not value of the noise, I mean the spectral density of the noise. What's that? Yeah, so if you consider only the thermal noise of this, it will be 1/8 kT times Gm. And how much is Gm? I mean, it depends on the region, but if you assume saturation region, it will be 1/8 kT times what? It is 2 ICP by the overdrive that you have chosen. Okay. Similarly, this will be GMP, right? So it depends on what overdrive you have chosen for the PMOS. Similarly, you will have noise of the NMOS transistor, whose thermal noise spectral density from the basic long channel equation is 1/8 kT GMN, which is 1/8 kT times twice the charge from current divided by that. Okay. Is this fine? Now, of course, this is in every cycle you are alternating between up and down, right? In the linear phase detector, you will have up for some time. I mean, basically you have up for half the time and down for half the time. Okay? So the output noise is basically a multiplex portion of the noise from here and noise from there. Is this okay? Now if you have only, I mean now this refers only to white noise, and let's for simplicity assume that the white noise spectral densities are equal, that is the overdrives are equal and so on. Okay? So then the multiplex white noise is the same as each of these white noises, right? This you can imagine, no? I mean, you imagine some value of noise here and then some other value of noise there. Okay, but if the two have the same variance, I mean same statistics, it will be like a single white noise process. Otherwise, if the spectral density here is different from the spectral density there, you have to take some kind of an average spectral density, because this is anyway getting low pass filtered by the transfer function, right? So if you take some sort of an average, let's say if this spectral density was 2 times this spectral density and each one is on for half the time, the effect will be the same as a single white noise source whose spectral density is 0.75 times that. Okay, it's the average of these two. Okay, so this kind of average picture is okay because this whole thing is anyway getting filtered by a low pass transfer function. Is this okay? So those things you have to do. Now by hand doing all of that when this and that have different spectral densities, it's possible, but it's a little messy. The simulators anyway, there are these periodic steady state simulations which will give you the right answer. Okay? Is this fine? So that will take into account the average and things like that. And also this may not be the exact expression for white noise. If it is in weak inversion, you will have a slightly different expression and so on. This is okay? And also on top of this, you will have flicker noise that will also be alternating between NMOS and PMOS. So you have to take the average of that as well. Okay? So all of that has to be done, but the bottom line is you can calculate the noise of the charge pump and then pass it through this transfer function. And at least if in the case where the easiest case is when you consider only white noise sources and the two white noises are the same, that is this and that have the same GM. Okay? In that case, you will have 8/3 kT GM as the spectral density of the charge pump noise, and this will get multiplied by this whole thing. By the way, this itself is 8/3 kT times 2 times the current divided by VGS minus VT times, first of all you have this factor, okay, and then you have this transfer function. Again, I think I should use omega BW here because omega naught I have been using for the frequency of transmission, right? Again, I made the same mistake. This omega BW refers to the bandwidth. Omega naught I have been using for the frequency of the clock. Okay. Maybe I have to change that notation. This is the spectral density of the clock due to the charge pump noise. Now if you express this as the phase noise, you have to take, because this 8/3 kTgm is a single sided spectral density, whereas the phase noise is 1/2 of that, right? So this will be 4/3 kT times the rest of the stuff. Okay? And also if you integrate this, you will get the variance of the phase noise here, which is 8/3 kT 2 times ICP by VGS minus VT. All these things remain the same. df times ICP by 2 pi square, and the integral of that is pi by 2 times FBW. Okay. So this is the integral of, this is the variance of the clock phase noise expressed in radian square. Okay. Now one thing you see is this whole thing is inversely proportional to ICP, right? Because you have ICP here and ICP square in the denominator. So the variance is inversely proportional to ICP. The spectral density is also inversely proportional to ICP. This is exactly what you expect with any circuit noise, right? We saw that we calculated noise of some circuits, and we saw that the spectral density or the variance will be inversely proportional to the current that you consume, right? So if you want to lower the noise from the charge pump, you basically have to increase the current. Okay. This is just like any other circuit scaling. Comes out in the same way. So it's true not only for voltage noise or current noise, but also for phase noise. Any questions here? What's that? Yeah? Meaning, the combination of PMOS and NMOS is that, right? Well, you will have other control circuitry, right? If you want, I can put the switches here, if this is what you are looking for. So the switches don't have to be in series with the current source, right? So this, essentially the upper current source, it should either pump ICP or 0. And one way to do that is, I can have a switch here. Okay. So let's say I have a current mirror to generate the current, and I can connect it to the bias voltage when it is up, and I can connect it to VDD when it is up bar, so that it becomes 0. So now, and the same thing here. So this will be down and down bar, and this will come from a current mirror. Okay. So in this case, if you only look at this part of it, there is only one NMOS and one PMOS. That is possible. But of course, you will have control circuitry. You have to have some control circuitry to control the currents. Okay. So there are many ways of arranging the switches. Some of them have, all of them will have some trade-offs. A fairly common thing is to use, this is the actual current source device, and you put the switch over there. Okay. This is okay? Switch? Yeah. The way the current source turns on and so on, there will be a difference. Any questions about any of this stuff? The point is you can calculate it. Like I said, all of these things become more crucial when you don't have the forwarded clock, but with this also it is important. Okay. And the main thing that you see is that if you want to reduce the noise contribution here, you have to increase the charge from current. Okay. And when you have different noise spectral densities here and there, and also include flicker noise, the calculation is more messy, but it can be done. Okay. Is this okay? Any questions? Okay, and then you also know the from phi ND to the output, what kind of transfer function will you have from the delay line noise to the output? What will it be? It will be high pass, basically. Okay, so this again, if the delay line is jittering very rapidly, then you can't track it. But if jitter is slow, then the loop will compensate for it. Okay, slow changes in delay, you can compensate for it. That's all. Okay, and you can calculate the output contribution from this, right? So we will revisit this when we come to other kinds of CDR. But basically, this is what you do, right? Now we can make some quantitative calculations. Okay. Earlier, we just came up with the topology. We didn't know how much ICP to use, how much C to use, and so on, right? So now we know a few things like the value of ICP and C essentially affect the bandwidth of the clock and data recovery. That is how fast of an input jitter you can track and so on, and the noise, etc. And then for a given bandwidth also you can see that what is the expression for the bandwidth. I don't know if I wrote it today, but we have it from the previous this one. And for a given bandwidth also, it only the bandwidth only depends on the ratio ICP by C. You can use a small ICP and small c, or a large ICP and large C. What is the trade-off now? No. I mean, it gives you the same bandwidth, right? I can use like maybe C is 10 picofarad and I can use a microampere, or 100 picofarads and 10 microamperes. What difference does it make? No. I mean, if the bandwidth is the same, why does it take more time to turn on? Noise is the only thing, right? So if you use larger current, you will have lesser phase noise that is generated in the CDR. Okay. So in principle, like as long as you maintain the ratio the same, it will behave in the same way. Okay. So that is the usual circuit scaling, right? You can make a low pass filter with a large R and a small c, or a small r and a large c. The difference between, the same bandwidth, the difference between them will be noise. Okay. So based on that you can calculate these things. And one other thing is density factor. You can see, for random data this will be half. You can kind of consider it as fixed. But if you do have cases where you expect like very few transitions, right? Then you have a problem everywhere. First of all, the bandwidth will be lower because it takes more cycles to correct it, and then also noise becomes higher. Okay, again the whole thing happens because you don't have enough information to go on correcting the phase. Is it okay? Fine. So now if you decide to do this with now we have done everything with a linear phase detector. What will happen with a bang phase detector? I can make the exact same circuit with a bang phase detector, right? So what will happen? How do I proceed with the calculation? What part of the model will change? Huh? No, the model. You look at the model here, what will change? What's that? Gain. So essentially, this so let's say I use a bang phase detector here. So if this is a bang phase detector instead, what will change? So basically, this is not a linear gain of df times ICP by 2 pi. What will that be? It should be a nonlinearity, basically a comparator, and essentially its nonlinearity is like this. It is either plus ICP or minus ICP depending on phi d minus phi ck. Okay. So now this is a nonlinear model, and essentially this is if you are taking data conversion type circuits, you will see that this is some sort of first order delta sigma modulator type model, right? You have an integrator and a comparator in the loop. So you can use the nonlinear model itself to calculate some things, but you can't define transfer functions the way we did earlier. Okay. But then in reality, I mean, what did you learn from the latest assignment? What was the first problem? There was something with the bang phase detector. What was it? Huh? Yeah, what about noise? So first of all, you will not get this type of average characteristics. On average, if there is jitter in the data, more specifically, if there is jitter between this data and clock, what happens is this bang detector, even if let's say data is supposed to be, if data is leading the clock, you are supposed to get basically a plus output all the time, right? But if it has jitter, sometimes it will cross over to the other side and you will get a lesser output. So the jitter itself has a tendency to, so this would be the characteristic without jitter. Okay. And you would have calculated that if you have a uniformly distributed jitter, you will have that characteristic. Okay. And then if you have a Gaussian type jitter, you will have some smooth characteristic like that. Okay. So the jitter itself linearizes this, and then so you will need to know the jitter. So this is kind of circular now. You will have to estimate the jitter between data and clock. Based on that, you can calculate the phase detector again. I'll just call it KPD. Okay. Instead of ICP by 2 pi, it will be some other number depending on the amount of jitter you have. Okay. The smaller the jitter, the higher the gain. So and then you can use that instead, you can still use a linear model with this KPD, but the KPD itself depends on the jitter. Okay. And from that you can calculate some of these things. So now with a bang phase detector, the operating point also includes the jitter, right? That is, on average, this whole thing, assuming it's working correctly, on average the position of a clock will be in the center of the data. Okay. But there will be some jitter between this data and clock, and that influences many of these transfer functions. Okay. How much jitter gets filtered, and then if you have a charge pump noise, how much jitter that causes, etc. These things depend on this linear characteristic, which in turn depends on the jitter between data and clock. Is this okay? So it's a little more complicated, but we'll still most of the time continue to use the linear model. For rigorous analysis, you have to consider the nonlinearity. Okay. Any questions here? But I mean, the bang detector does have some unique features that will not be there in the linear phase detector. It's not just a mere change of gain. Okay. So it's not that you replace ICP by 2 pi with some new KPD and everything will be exactly the same. But qualitatively it is different, and it will have some features that was not there with the linear phase detector. We'll look at that. Okay. So please think about these things, and we'll continue with clock and data recovery. But now we will eliminate the forwarded clock and then see how to recover the clock by using only the data. Okay. This is what? Bang? No. The bang. So this is some sort of average behavior, but the bang jitter will be there. We'll see how much bang jitter will be there.